We use the term space truss to refer to a 3D truss. Pin joints in 2D become ball and socket joints in 3D, since the latter permit rotations in all directions and therefore can only transmit forces. As with our 2D problems, the key assumption is that the space truss can be treated as an assembly of two force members. Method of joints and method of sections are both useful in space truss problems. Since 3D particle equilibrium provides three independent equations, we look for joints where there are three unknowns as a starting point to establish a joint sequence. If using method of sections in 3D, we can write six independent equilibrium equations, three each in force and moment equilibrium, so we look for cut planes through the structure that cut through no more than six members. Because 3D equilibrium of a body involves six independent statements, it is especially important to look for points to take moments that simplify the equations and make solution of those equations easier. Determination of partial fixity in a space truss problem is often much more difficult than that of a 2D problem. In this case, the structure as a whole is supported by ball and socket joints at D, E, and F. This provides a total of 9 reaction forces, which seems like more than enough to ensure structural fixity. What is often difficult to see, however, are those modes of movement within the structure, even if the structure is anchored at points like D, E, and F in the XY plane. Here it may be helpful to consider pin supports in 2D. I'll make a note here in 2D. Suppose we have a couple of pin supports here, and we have a structure that looks like this. This is not a stable configuration because this is going to have a rotational mode. In this case, it's going to be possible for this to assume a shape like this very easily. So this whole thing can move like this and is not stable. In 2D, what we do instead is to use triangles as stiff structural elements. So we could replace our original configuration this way with one like this and take care of that rotational issue. The structure analogous to the 2D triangle is the 3D tetrahedron. This is a solid element with 4 triangular faces, and it does not admit rotations. In contrast, a pyramid, or a pyramidal element, a 5-sided element with a square or rectangular base and 4 triangular faces meeting at an apex, does admit rotations. Returning to example 1, we can see one tetrahedral element in the assembly, defined by vertices A, E, B, and C. In this case, the triangular face ACE here can be thought of as the interface between the stiff tetrahedral element and the rest of the structure. As we'll see shortly, there is a rigid body motion within the structure involving the tetrahedral element pivoting about axis BE, aligned with the z-axis. At the end of section 6.2, we presented a rule of thumb involving the number of reaction components, number of joints, and number of members of a truss. This can be extended to space truss problems where we compare M plus R to 3J instead of 2J in 2D. In the present case, we have 8 members, 9 reaction components, 3 each for each of the ball and socket joint supports at D, E, and F, and 6 joints. In this case, M plus R is 17, less than 3J equals 18, and this suggests partial fixity or a mechanism. Here we can actually see that mechanism in a movie. Notice the tetrahedral element is pivoting about member BE. Unlike plane trusses, where mechanisms can often be identified by inspection, it can be very difficult to identify mechanisms in space trusses. The remaining bullets speak for themselves, but perhaps we can restate the last bullet in a different way. Designing a space truss as an assembly of tetrahedral elements prevents the development of mechanisms inside the overall truss. You can see this sort of design in the lattice work of crane booms at construction sites. Here we have a truss almost identical to that in example 1, except that an additional diagonal member CD has been added to the truss. Using our rule of thumb, we now have m plus r equals 18, matching 3j equals 18, which suggests static determinacy. We can also see how the addition of CD eliminates the rigid body motion we saw in our earlier movie. A pivot in the plus z direction about member BE brings joint C forward into the plus x space above the yz plane. But such a movement requires a shortening of member CD, violating our rigid body treatment of members. The presence of CD blocks the rotation and eliminates the rigid body motion. Having confidence in both the integrity of the truss and its static determinacy, we're now left with the question of how to begin. Here, imposing equilibrium on the entire truss is not a good way to start, since we have 9 reaction components and 6 equilibrium equations. This leaves us with beginning with either a joint or a section. Using the method of joints, we can see a path or joint sequence to finding the force carried by each member. We have 3 unknown member forces in joint B. Establishing equilibrium at that joint allows us to find the forces carried by members AB, BC, and BE. Having obtained the force carried by member AB, we can bring that information over to joint A, where we can solve for the loads carried by members AD, AC, and AE. Finally, having obtained forces carried by BC and AC, we can bring that information over to joint C, where we can solve for the loads carried by members CD, CF, and CE. Our joint sequence is B to A to C, and we now go about carrying out the details of the solution. One of the things we haven't discussed yet in space trusses is the extension of zero-force member criteria. As it turns out, this problem, example 2, is a great vehicle for doing that. Instead of looking at the free body diagram of joint B from the perspective view shown in this slide, let's look at it from above, in the positive z-space looking straight down at the xy plane. The free body diagram from that perspective would look like this. Our coordinate system now has x, and from this perspective, x is this way, y is this way, and we'll just make a note here that z is out of the plane. And we have 2 forces acting at this point, which from this perspective will only allow us to see their tails. So I'm going to place the member force here in black, and I'll put the actual load in red. These should be coincident here, but I want to make this distinction between them. So we'll make a note here that these represent the tails of TBE, and the 6 kip load. Note that this looks exactly like one of our cases of zero-force members from the discussion of 2D trusses. TBC and TAB both lie in the XY plane. Both the 6-kip load and TBE are aligned with the z direction, so they are both irrelevant to equilibrium in the xy plane. Since there is no external load in the xy plane, equilibrium in the x and y directions tells us immediately that TBC and TAB are both 0. It is also the case that z equilibrium tells us that TBE is minus 6 kip. That is, member BE is carrying a 6 kip load in compression. Before proceeding to joint A, we can generalize our zero-force member criteria for space trusses. Let's consider this perspective view here. I'm going to bring a total of 4 members into a joint that's established at the origin here. Let's make a contrast. Here we're going to have joints A, B, C, and D, all lying in the xy plane. So members AD, BD, and CD are coplanar. And then we're going to have a member DE, which is not coplanar. So the projection here of DE in the xy plane is going to make an angle alpha. If we have n members coming together at a joint, and n minus one of them are coplanar, and there is no external load at the joint, or more precisely, there is no external load with a component in the non-coplanar direction, then equilibrium normal to the plane requires the non-coplanar member, in this case DE, to carry no load and be a zero-force member. Now let's proceed to joint A. Let's look at this first from the positive x space, looking straight down at the YZ plane. Furthermore, since we've just shown that TAB is a zero-force member, we'll not include that member in the sketch. Of the 4 remaining loads or member forces in the sketch, only TAE has a y component of force. Of the 4 remaining loads or member forces in the sketch, only TAE has a y component of force. Imposing equilibrium in the y direction immediately tells us that TAE is also a zero-force member. Now look at joint A from the positive y space, looking straight down at the XZ plane. Since we've established that both TAE and TAB are zero-force members, there is no need to include them in the sketch. Imposing equilibrium in the x direction tells us that TAC is a zero-force member. Imposing equilibrium in the z direction tells us that TAD carries a compressive load equal to 4 kip. We could carry these results over to joint C and repeat the exercise, and we would find again that CD and CE are zero-force members, and that CF carries a compressive load equal to 5 kip. This problem is unusual in that all the loads are vertically oriented, and so we got a relatively simple result. 6 of the 9 members are zero-force members, and the 3 remaining members are carrying the imposed loads in compression. Had the loads not been purely vertical, we would have had a more complicated result, and most, or perhaps all, of the members would be carrying some load. Our joint sequence from B to A to C would still serve its purpose. There would just be more algebraic manipulation at each step.